Students find that writing proofs of convergence statements tends to be one of the most difficult parts of a real analysis course. Understanding the structure of these proofs and having a few techniques is a helpful starting point, but nothing can replace the time spent thinking and struggling through the proof writing process. One important idea to have in your mind is that proofs involve a bit of exploration and creativity. You need to give yourself the freedom to try different manipulations and fail at them. There's nothing more limiting to a student's cognitive development than an unwillingness to engage in mathematical experimentation, which is why we read the Rubric for Creativity in Writing Proofs article a couple weeks ago. In order to write a successful proof, you need to know where your starting point and your ending point are. Since we're writing proofs about convergence, we should begin with the definition. Definition: a sequence S sub n of real numbers is said to converge to the real number s, provided that for each epsilon greater than 0, there exists a number capital N such that little n greater than capital N implies that the absolute value of s sub little n minus s is less than epsilon. This statement represents the property a sequence must satisfy in order to converge. Reading the definition this way can make it hard to distill out the primary features, so we will look at the definition in pieces. A sequence S sub n of real numbers. This sets up the definition by establishing the type of object under consideration. We are working with sequences. Notice that this also sets up the notation for our sequence. Is said to converge to the real number s. Not only are we talking about convergence, but we also have a symbol s that represents the value the sequence is converging to. Provided that. This is a key phrase in definitions where you transition from the setup to the actual condition that the word represents. The next three phrases are where students' eyes start to glaze over as they start to feel lost in the sea of mathematical notation. So rather than taking this head on, we will look at the structure of this property. For each x, there exists y such that z. The phrases for each and there exists are known as quantifiers, and they give you guidance about how your proof should be structured. For each x, you should imagine x as a box that contains a lot of objects in it. The quantifier for each simply means that no matter which object you happen to grab from the box, it's supposed to have some sort of property. There exists y. This is the property that your object is supposed to have. After you grab some object from the box, the property is that there's some corresponding object somewhere else in the universe that meets some condition. But what is that condition? Such that z. Z is the defining characteristic of y. Here is a tangible example of this phrasing. For each ball in the box, there exists a person that holds the corresponding number. The basic idea here is that of a raffle. In order for this statement to be true, no matter which ball you draw, there must be someone out there holding that number. If there's a single ball in the box for which there is no winner, then the statement is false. And that's how you should think about statements of this form. Let's return to the definition of convergence. A sequence S sub n of real numbers is said to converge to the real number s provided that, for each epsilon greater than 0, for every single positive number no matter how small, there exists a number n, you can find a very big number called n, such that little n greater than capital N implies that the absolute value of s sub n minus s is less than epsilon. If you go far enough out, all the terms in the sequence are close to s. In other words, no matter which random numbers you draw from the box of epsilons, there is some number capital N that has the winning property.
Now that we know what a proof of convergence entails, we know exactly how it should be structured. Every proof of convergence will have three sections corresponding to the three parts in the definition. The first thing every proof needs is the phrase, let epsilon be greater than 0. This corresponds to picking an arbitrary epsilon from the box. The next section will have the phrase, let n equal something. Figuring out which n to choose is the hard part of most of these proofs. Sometimes your n will be an explicit formula in terms of epsilon, and other times your n is going to be chosen based on properties that you developed throughout the proof. The last part of the proof is a verification step. You need to show that the absolute value of s sub n minus s is less than epsilon given all the properties that you've developed so far. In class, we will work through examples from beginning to end so you can see how this process works.